Hello, my name is Victoria Faircloth. I'm going to be doing my presentation on seafloor spreading. Seafloor spreading introduction. Seafloor spreading is a process that occurs at mid-ocean ridges where new oceanic crust is formed through volcanic activity and then gradually moves away from the ridge. Seafloor spreading helps explain continental drift and the theory of plate tectonics. Seafloor spreading produces basalt. Seafloor spreading is one of the two major processes of plate tectonics. Seafloor spreading ends when mid-ocean ridges are subducted. Discovery of seafloor spreading. Harry S. Truman is a big name when it comes to seafloor spreading. Harry S. is the person that discovered that the seafloor was spreading. Seafloor spreading was first proposed in the early 1960s by the American geologist Harry H. S. Magma is melted rock below Earth's surface. A mid-ocean ridge is a mountain range in the middle of the seafloor. Evidence of seafloor spreading, oceanic ridges and seafloor spreading, and magnetic reversals in seafloor spreading. Abundant evidence supports the major contentions of the seafloor spreading theory. First, samples of the deep ocean floor show that basaltic oceanic crust and overlying sediment become progressively younger as the mid-ocean ridge is approached, and the sediment cover is thinner near the ridge. Second, the rock making up the ocean floor is considerably younger than the continents, with no samples found over 200 million years old, as contrasted with the maximum ages of over 3 billion years for the continental rocks. This confirms that older oceanic crust has been reabsorbed in ocean trench systems. Some extra information on seafloor spreading. By the mid-1960s, studies of the Earth's magnetic field showed a history of periodic reversals in polarity. A timescale of normal and reverse polarity was reestablished, showing 171 magnetic flip-flops in the past 76 million years. Typical rates of spreading average around 5 centimeters, 2 inches per year, roughly the same at which human fingernails grow. In 1963, Fred Vine and D.H. Matthews demonstrated that the high and low intensity stripes supported the concept of seafloor spreading. Vine and Matthews suggested that the stripes of high-intensity magnetism are regions where the paleomagnetism of the ocean crust exhibits normal polarity. Consequently, these rocks reinforce Earth's magnetic field. Conversely, the low-intensity stripes are regions where the ocean crust is polarized in the reverse direction and therefore weaken the existing magnetic field. Vine and Matthews reasoned that as magma solidifies along narrow rifts at the crest of an oceanic ridge, it is magnetized with the polarity of the existing magnetic field. Because of seafloor spreading, this strip of magnetized crust would gradually increase in width. Seafloor spreading produces major characteristics of the seafloor. 1. The age of the seafloor is progressively older away from mid-ocean ridges. 2. The elevation of the seafloor is progressively lower away from mid-ocean ridges. 3. The magnetic history of the seafloor bears the striped pattern of the Earth's magnetic reversals. And 4. Older parts of the seafloor have the greatest potential to have accumulated sediments over the longest time. Seafloor spreading determines plate motion around a mid-ocean ridge. Wherever the seafloor is spreading, the edges move apart while the magma in the middle hardens. In the general case, seafloor spreading starts as a rift in a continental landmass, similar to the Red Sea East Africa rift system today. The process starts with heating at the base of the continental crust, which causes it to become more plastic and less dense. Because less dense objects rise in relation to denser objects, the area being heated becomes a broad dome. As the crust bows upward, fractures occur that gradually grow into rifts. The separated margins of the continents evolved to form passive margins. To first approximation, seafloor global topography in areas without significant subduction can be estimated by the half-space model. Comparatively slow spreading rates of 2 centimeters per year are found along the mid-Atlantic ridge, whereas spreading rates exceeding 15 centimeters, 6 inches per year have been measured along sections of the East Pacific Rise. Although these rates of seafloor production are slow on a human timescale, they are nevertheless rapid enough to have generated all of Earth's ocean basins within the past 200 million years. The primary reason for the elevated position of the oceanic ridge is that newly created oceanic lithosphere is hot, which means it is less dense than cooler rocks found away from the ridge axis. As soon as new lithosphere forms, it is slowly yet continually displaced away from the zone of upwelling. The Pacific Ocean covers 1/3 of the planet, but it is shrinking. Even more evidence of seafloor spreading and even more information about seafloor spreading. A veritable legion of evidence supports the seafloor spreading hypothesis. Studies conducted with thermal probes, for example, indicate that the heat flow through bottom sediments is generally comparable to that through the continents except over the mid-ocean ridges, where at some sites the heat flow measures 3 to 4 times the normal value. The anonymously high values are considered to reflect the intrusion of molten material near the crest of the ridges. Research has also revealed that the ridge crests are characterized by anonymously low seismic wave velocities, which can be attributed to thermal expansion and microfracturing associated with the upwelling magma. Investigations of oceanic magnetic anomalies have further corroborated the seafloor spreading hypothesis. Such studies have shown that the strength of the geomagnetic field is alternately anonymously high and low with increasing distance away from the axis of the mid-ocean ridge system. The anomalous features are nearly symmetrically arranged on both sides of the axis and parallel the axis, creating bands of parallel anomalies. Measurements of the thickness of marine sediments and absolute age determinations of such bottom material have provided additional evidence for seafloor spreading. The oldest sediments so far recovered by a variety of methods, including coring, dredging, and deep-sea drilling, date only to the Jurassic period. That is, they do not exceed 200 million years in age. Such findings are incompatible with the doctrine of the permanency of the ocean basins that have prevailed among Earth scientists for so many years. The mid-ocean ridge is the longest chain of mountains in the world. In the 1950s, scientists mapped the mid-ocean ridge using sonar. Sonar is an instrument that uses sound waves to measure distance. It bounces sound waves off underwater objects and records the echoes of these sounds. The time that it takes to echo indicates the distance to the object. The scientists found out that the ocean floor was not flat. This discovery piqued their curiosity to discover what the ridge was and how it got there. In the 60s, scientists used a small submarine ship called Alvin to explore the ocean floor. Alvin's crew found rocks shaped like pillows or toothpaste squeezed from a tube. These rocks showed that molten material had erupted many different times from cracks along the mid-ocean ridge. The Earth is like a giant magnet with a north and south pole. The Earth's magnetic poles reversed themselves 780,000 years ago. Molten material contains iron. As it is cooled, the iron bits line up in the direction of Earth's magnetic poles. When the rock hardened, the iron was locked in place, giving the rocks a permanent magnetic memory. Scientists recorded this magnetic memory on both sides of the mid-ocean ridge. Rock that hardens at the same time would have the same magnetic memory. The Glomar Challenger is a drilling ship that recovered drilling samples from the ocean floor. The ocean floor plunges into deep underwater canyons called deep ocean trenches. Subduction takes place where there are deep ocean trenches. New oceanic crust is hot. It moves away from the mid-ocean ridge and cools, making it denser. Gravity pulls the denser, older crust down beneath the trench. Subduction allows the ocean floor to sink back into the mantle that takes tens of millions of years. There is a ring of trenches that surrounds the Pacific Ocean. This occurs because the deep ocean trench follows more oceanic crust than the mid-ocean ridge can produce. If new crust is not added fast enough, the width of the ocean shrinks. The Atlantic Ocean is expanding. The Atlantic Ocean has only a few trenches. The Atlantic floor is attached to the continental crust of the continents. As the seafloor spreads, the continents along that edge also move. In 1960, Harry Hess studied Wegener's theory. Hess proposed the radical idea that the ocean floors move like a conveyor belt, which in turn move the continents. Seafloor spreading begins at the mid-ocean ridge, which forms along in a crack in the oceanic crust. At the mid-ocean ridge, molten materials rise from the mantle and erupt. The molten material spreads out, pushing older rock to both sides of the ridge. Rocks on the ocean floor are in a pattern of magnetized stripes. Reversals happen on average only about once every 250,000 years, and they take hundreds if not thousands of years to complete. The need for evidence in science has not changed. Without evidence, we just have theories and hypotheses which cannot be supported without evidence to back them up. Seafloor spreading and other tectonic activity processes are the result of mantle convection. Mantle convection is the slow churning motion of Earth's mantle. Convection currents also recycle lithospheric materials back to the mantle. Seafloor spreading occurs at divergent plate boundaries. Seafloor spreading is not consistent at all mid-ocean ridges. Slowly spreading ridges are the sites of tall, narrow underwater cliffs and mountains. Rapidly spreading ridges have a much gentler slope. Subduction is the other part of plate tectonics. Seafloor spreading creates new crust. Like I said earlier on in this presentation, subduction does just the opposite. The two forces roughly balance each other, so the shape and diameter of the Earth remains constant. Some things that seafloor spreading includes. Some things that seafloor spreading includes is the idea of convection and convection currents, deep ocean trenches, and mid-ocean ridges. Convection is the name for a means of heat transfer as distinguished from conduction and radiation. A convection current is the transfer of heat by the mass movement of heated particles into an area of cooler fluid. A deep ocean trench is a portion of the Earth's crust in which a tectonic plate is being subducted, pushed down below another plate. Finally, again, a mid-ocean ridge is an underwater mountain system formed by plate tectonics. Convection is also a term that describes processes affecting the atmosphere, waters, and solid Earth. Another thing about convection is that convection is related closely to heat and temperature and indirectly related to another phenomenon, thermal energy. Convection currents in the magma drive plate tectonics. Deep ocean trenches are large linear depressions that are remarkably long and deep. The mountains of the mid-ocean ridge are linked in chairs, typically having a valley known as a rift running along its spine. This type of oceanic mountain ridge is characteristic of what is known as an oceanic spreading center, which is responsible for seafloor spreading. The production of new seafloor results from mantle upwelling in response to plate spreading. The isentropic upwelling solid mantle material eventually exceeds the solidus and melts. Thank you for watching my video on seafloor spreading. I hope that you have gained a lot of knowledge about seafloor spreading from this video.